Hey guys, welcome back to AlgoYogi. We are doing tree series right now, and our next problem in the list is unique binary search trees. Second, we have already solved the first problem. Please check it out if you have not solved it. I would recommend you solve it first and then come to the second problem. All right, let's go to the problem on LeetCode. Okay, so the description is given an integer n, return all the structurally unique binary search trees which has exactly n nodes of unique values from 1 to n. So it's not from 0 to n minus 1, it's 1 to n. So let's take care of that when we are solving it. Return the answer in any order. So that doesn't really matter, but now for our first example, they have given us n equals to 3. All right, so let's go to let's change our view here. Let's try to understand what's being asked. So for first example, we are given n equals to 3, and in the previous question, which is unique binary search trees, we were supposed to return a number, an integer, which is the number of unique binary search trees we could create using 3 nodes, or like in this example 3 nodes, and the answer was basically 5. But now we're not returning 5, we are returning the root for each of those 5 unique binary search trees. Crazy, right? Like how are you going to do that? That's really simple. You know how even while calculating the number of trees, we have done the same logic. It's just from the place where we were adding one more, those combination from left and right for each particular root that we are choosing. Now we have to do is create that root, create those combination of left and right, return the root, or maybe add it to our answer, and then return the answer. That's it. Okay, let's understand how we're going to do that. So that's like a bigger picture, but let's dive deep in how we are actually going to do it. So in this example, we are given n equals to 3. That means what? That means we have our nodes available. The nodes available to us are 1, 2, and 3. Now, since we are going to create binary search trees, we can't just append left and right in any order. It's like when we are choosing a root, we have to take care of that left can only take the smaller values from what the root value is, and right can only take the bigger values. So in order to create different trees, different binary search trees, we're going to pick roots one by one. So if I pick 1 as my root, that means what? My left cannot take any value, so that will be none. But my right can take 2 and 3. But now tell me, this itself is again like a smaller problem. We're just simply asking this should also return us the number of unique binary search trees, right? Exactly. So this will give us 2 different binary search trees. Exactly, right? Like this is also a sub problem, isn't it? Just like we are solving this main problem, this is also a sub problem, and this should also return, and we're going to tackle it in the same manner that we are tackling our n equals to 3. Here n equals to 2, so which means I can choose 2 as my root, so 3 will take right and left will be basically none. Or I could choose 3 as my root, and then my left will be 2 and right would be none. All right, these are the 2 trees we can create. So from left, when we're choosing 1 as my root, that means what? For this none, I could basically choose one of these right subtrees. So you see, when I'm choosing one as my root, I could create basically two combinations from left and right. So for each value in left, I am basically choosing one value from right. So it's like I'm creating combinations. So you can imagine we'll be using for loops, two for loops, basically for left and for right, and then we will be matching them, and then we are appending it to the root. Exactly. And then for that root, how we will create a lot of combinations, and each time for each left and right pair, we will be appending that root to our result. All right, so and same thing we're going to do with when we are choosing 2 as our. So this is when we are choosing root is 1. Now when we have root as 2, then I think we only have one possible binary search tree, because it's only one value in left and one value in right. So you can't really make any other pairs, right? Because you can't send 3 to the other side or 1 to the other side, and there are no more values to like create more combinations on left and right. But when we choose 3 as root, when root is 3, then we can actually create 2 more trees, which is when 3 is root. So right will take none, because there is no value that's greater than 3, and then left would be 1 and 2, and we know when n is equal to 2, that returns, we have already seen it, 2 trees. All right, basically when 1 is root, which is like this, and when 2 is root, so it would be like this, and these trees will make combination with none each, and then will return basically 2 different binary search trees. I think now it's very, very clear. And the time complexity for this problem is like little weird. It's not weird, I think it's not something that will be asked to us, right? So but I'll write it down. The time complexity would be 4 to the power n root n. So I don't know, I'm not gonna drive it, and to be honest, I don't even know how to drive it. And they have said in the problem that like it's not gonna be asked because it's quite complicated to drive. But what's not complicated to drive is our answer. Let's write it down because we have already done it. All right, so let's focus over here. I'm going to create a helper function, and I'll call it create, let's just call it BST. All right, that is going to take left and right pointer. That's because that's the range of values we have. Initially it will be 1 to n, all inclusive. We'll take care of that. So if my left pointer is greater than my right pointer, that means what? That means I'm done. I do not need to create any more like trees using these, because I ran out of the values. So I can just return, since we're returning list, so it will be better for us to return it as list. Now, as we said, like we're gonna choose each value as our as a root. All right, and for that root we will create combinations from left and from right, and then mix, and for each combination we will have this same root. Like, okay, let me just call it value. For value in range, I think this will make it really clear, and that is basically between left and right. And let me add 1 because it's exclusive. We want to include n, especially if we are sending from 1 to n, then we have to add one one there because we want to include it. Now let's create our root. Root is basically tree node, and we're sending in the value. All right, but we have to generate all the binary search trees, unique binary search trees for the values that are now going to be in the left subtree and also in the right subtree, so that we can make combinations of those two groups, right? Okay, so for, let's say, left tree in, we're going to basically send this. We're going to call the recursive function, and this time left will remain same and right will be basically value -1, because we have already used value to create our root, right? And then let's do the same thing for right tree. All right, right tree. Okay, but this time right pointer will remain intact, only basically left will be value +1. All right, now these are returning left and right subtrees. Combination is ready. Let's move our root inside these, because root is common. We just don't want to, like, again and again put in the value. So root will be value and left tree and right tree. That's one of the ways of creating it. You can see over here in tree node, if you, in place of left and right, you can send the left tree or subtree or root, and this should give you the complete tree. All right, so left tree and right tree. And finally, let's add it to our answer. Let's call it result. Let's create it outside, and we're going to append it to our res.append our root. All right, and finally, once we are done creating all those combinations, we can come out of our main for loop and just return result. All right, and this will take care of that case when left doesn't have any values and it's just one value, which is none, and tree with none value will be just none. Tree, if you send none into tree node, that will be none. So that's all good. Finally we can call our create BSL, and in place of left and right pointer we can send 1 and n. All right, so let's try to run this answer and submit it. All right, this passes the tests. Let's submit our answer. This is quite efficient, but we can do one more improvement here, since it's a recursive function, and there might be cases where for each combinations we are doing some repetitive work. So let's have some memo, and memo will basically be each time for all these combination for left and right, we can just simply store that into memo. So if let's say if L, R in my memo, then I will just return memo L and R, and let's save this answer here. So memo left and right, and the answer would be here, res. Right, and instead of returning res, we can just return, we can return res, or we can return this, and that should be good. So let's run this memoized version, and not like this. So it's a value, we're accessing from our dictionary. So my bad. All right, and let's see if it's going to improve any. No, so not really. But anyway, but we know what we are doing. Okay. All right, let's go back to AlgoYogi and mark our problem solved. Please like, share, subscribe if this video helped you, and start making use of AlgoYogi to track the problems you are solving. You can basically, the categories are here. We have solved 37 problems so far. We have solved way more. It's just I haven't marked the problem that I've solved in array string hashing. I'll do them later because I was recording them in Hindi, just having some bakchodi over there. But I realized that it's better to record these videos in English so that they can reach and help a larger audience. But anyway, thank you. See you guys in next problem. Until then, bye bye.